here, right? You just need a left meter. You don't have to sign over my race. You will not work. So I'll leave the attendance sheet over here. Later on after class, you can come again. Okay. This will be the last part for your first topic. So the first topic is on tree vibration.
Ready? Go lah, you think school very school.
So this one is about measuring the damping ratio. And yeah, I forgot to say that next week you will have your you're gonna have your lab 2 weeks later. 2 weeks later you're gonna have your lab. Have a look into your Moodle. So all of you will be organized into groups of 3, sometimes 4, yeah. And your lab is gonna be over in Dover side. Yeah. So if you don't know the name Dover, the name before, you want to know all these combinations, go and find it out. Yeah. Dover side. So that includes your lab sheet is already in there. Lab sheet will be submitted individually. Okay, so download that and make a printed copy for yourself. I think it's good to show you that so that you know. So this is the Moodle. If you go up there, you can see all those information that are already uploaded. So that will be tutorials and practice questions. This is your first assignment. Right? The deadline is on 23rd, 5 p.m. strictly. And then I also uploaded practice questions for you. Right? You can't really see very well. And then there's a lab experiment. So you have the grouping. So the AD students, you'll go in the morning on the 25th of October. AS, you'll go in the afternoon on the 25th of October. So the lab sheet, you can find it here. So let's have a look at this topic. The underdamped system is given by this equation, and I'm going to rewrite it. That's your underdamped system. Now, if I were to sketch this underdamped system, that means this equation over here, sketch it on this axis. This one is time t, and this one would be the kind of y-axis that in this case is your time response. So if I were to sketch this equation, I'll end up with this kind of curve. Yeah, and then you kind of like wiggle. So if I were to go ahead and label this point over here, this is your x naught, the same x naught as this. Okay? That means from this point 0 along the y-axis all the way to this peak, this is x naught. And if I were to call this one period, right, so you go up, come down, and up again at time t1, and I call this amplitude over here x1. This point here, t2, I call this amplitude over here, right, this amplitude. This one is x2, and this part over here, x3 at t3. All these are talking about amplitude. Maybe it's easier if I do the arrows consistent. This amplitude, and at this time t2. So that's the equation. That's the equation of x t. Right? It will go up and down. And there are a few other characteristics. This curve over here, it would decay along this kind of line. It would decay both at the positive and symmetrically negative side. Right. So the top part, that dotted line, it has an equation. That equation is x naught e to the power minus zeta omega n t. That dotted line that's at the bottom is minus x naught e to the power minus zeta omega n t. So that x naught e to the power minus zeta omega n t, you can find it in the original equation over here. This is what we call the amplitudes of successive oscillation. So you can see successive oscillation, this first one over here, this one is x naught, second one x1, x2, x3. If you look at the set of notes that was provided to you, Glasgow labeled this as x1 from here. I prefer x naught because so that it's consistent with your lab. Your lab is also x naught. So you can name it any convention, start from x naught or x1. So I kind of prefer to call this as the zero peak, first peak, second peak, third peak in that way. Right. So some textbooks, they will call this as first peak, second peak, third peak, fourth peak. I prefer to call this as your zero peak. So this period over here, that will be your tau d. So your tau d is your period of damped oscillation, and tau d, it has a formula to it, 2 pi over omega d. And successive peaks over here, they are all tau d, all equal in length or equal in time. This is along the time axis. All these are tau d, and they are equal to 2 pi divided by omega d. Now, if you are worried about a lot of these new things coming in, and then you're wondering, well, do I need to memorize all this because they are all very new to me? No, you don't have to. I put it in your data sheet over here, including this tau d over here, and all these curves that you can see. How nice! Right? You can't see that over here. Look at that.
Look at that.
Right, so it's ready in your data sheet. So what I need to do is that, remember, this topic here is to find out what is the damping ratio. Damping ratio is zeta. Right? So it's called the damping ratio. How can I find out damping ratio from a graph like that? So I need to do some mathematics. At time that's equal to t1, that is this time over here, x1 is equal to x at time t1. What that means is that we want to substitute t1 into this underdamped equation over here. So if I were to do that, then this will be x0 e to the power minus zeta omega n, and that t now becomes t1. And I wouldn't substitute t1 into the rest of it, right? Why wouldn't I do that? Because t1 is actually the time that's equal to tau d. So tau d is the time that takes from here to here, which is also equal to t1, right? So that means this t over here will be 2 pi over omega d. Yeah. So omega d and omega d will cancel off. Cosine 2 pi, what do you get? Cosine 2 pi. Cosine 2 pi is equal to 1. So this whole thing will become 1. The same thing, this will be sine 2 pi. Sine 2 pi is equal to 0. So this term will be gone. This term is equal to 1. So I don't have to put anything over here. It's kind of like multiplied by 1 here. So after that, I want to find out at time that's equal to t2 such that t2 is equal to t1 plus tau d. So you can see t2 is here. So t2 is taking t1 plus this entire time, that is tau d. So where is tau d is equal to 2 pi over omega 2, and this is your period of then oscillation. And the units for that, for tau d, is seconds. So if you have seen this formula before, some of you may remember it. We have seen something very similar before. So if I were to show you again, so just now that data sheet that I have, this one is tau d. That d there tells you that it's a there's a damper inside the system. That's why d damping. If there's no damper, that means it refers to the previous page. Simple harmonic motion. And this part here is your tau n. So if I zoom in, tau n, oh there's no n, anyway, 2 pi divided by omega n. And you would know that because your graph over here, you can see that there's no decay at all. Let's keep on going. So there's no damper. Okay, that's how you know. There's no damper, so your oscillation will keep on going. In your schematic sketch, if you don't see any damper in there, that means there's no chance that it would damp. Right? There wouldn't be a hidden air friction damping thing. If there is that kind of thing, it will be represented by a damper. So if there's no damper, then it's a harmonic motion. So I'm still after to find out what is my zeta. So after I have that, x2 will be equal to x t2. And x t2 is substituting again into my underdamped equation. So that will get me x naught e to the power minus zeta omega n. This will be t2. Because I want to find out what's the x when it's at t2. So the rest of the sine and cosine term, as what we've seen before, is actually equal to 1. So we don't have to prove that. So this t2 is actually equal to t1 plus tau d. So if I were to now take the ratio of x1 over x2, I want to take this ratio. So x1, we saw it. This is your x1 expression. So I write it down. x0 e to the power minus zeta omega n t1 over the x2 expression. I'll write down as well. x0 e to the power minus zeta omega n t1 plus tau d. This denominator can actually be simplified. So let me simplify that. x0 e to the power minus zeta omega n t1 multiplied by e to the power minus zeta omega n tau d. This is your law of indices, yeah? If you remember, the law of indices. So you can see that this and this, you can cancel it out. So what is left? x1 over x2 is equal to e to the power minus zeta omega n tau d. No, I don't think there's any more minus because this is your denominator. There's no more minus there. Because 1 over e to the power minus something is the same as e to the power of that something without your law of indices. Yeah. So now that you have that, the next thing to do is to take ln, natural ln on both sides that are represented by this L. Natural ln is different from log, L-O-G, logarithm. Logarithm is to the base 10. Natural log, or ln in this case, is to the base e. Right? So taking ln on both sides, what that means is ln on left hand side, ln on right hand side. If you take ln e to the power of this, you get this. Right? That's your logarithmic rules again. So once you have that, I want to substitute tau d. So tau d is 2 pi over omega d. And I also know that omega d is actually equal to omega n square root 1 minus zeta squared. Right? As in your formula sheet, your omega d is equal to this. So this allows me to cancel away omega n. So eventually, if I write it out, ln x1, x2 is equal to 2 pi zeta over square root 1 minus zeta squared. That 2 pi, I'll bring it to the left hand side. Ln x1 over x2 zeta over square root 1 minus zeta squared. So you can see how many unknowns there are. This 1 over 2 pi is constant, right? It's not an unknown. x1 is unknown, x2 is unknown. And right hand side, only zeta is unknown. So what that means is that for this part, if x1 and x2 are known, then zeta can be determined. Right? So if you look back at the graph again, I can shrink it so you can start to see the graph. Right, if you look at this graph, x1 is here, x2 is here. If I'm able to measure that, that means if I have this string, right, and then it oscillates. So that first coming up, down, up, down, up, until it settles at this neutral position. So that first oscillation going down, coming up, right, that part over there, from that neutral position, if I can physically measure that, that's my x1. And then it will continue to oscillate, and then coming up a little bit less, that one, my x2. If I'm able to measure that x1 and x2 physically, then I will know what is that ratio, x1 or x2, just by measuring. And if I'm able to measure that, calculate x1 over x2 ratio, there's only now one unknown, that is zeta. And I can calculate what is zeta. What's the big deal about zeta? Zeta is actually a big deal. Because if I know that value of zeta, if it's less than 1, it means it's an underdamped system. If it's more than 1, it means it's an overdamped system. And then if it's equal to 1, critically damped system. So just by knowing what is zeta, we'll be able to know what kind of system we're dealing with. And after I know that, then I will know what is its general form. And no way out. So that's why zeta is very important to us. So some of you may be wondering, you'll be wondering like, hey bro, I can see what you mean. That was awesome. You took x1 over x2. How about if I take the case of x1 and x3, that ratio, x1 over x3, would it work? Let's have a look. Very good question. Alternatively, x1 over x3. So that's x0 e to the power minus zeta omega n t1 again, and then x0 e to the power minus zeta omega n. This will be t1 plus 2 times tau e, right? Because that's where x3 is 2 times 1 of tau t, right? The time here, 2 times 1. And I'll show you over here. So this t1. So t3 is over here, and this whole thing is 2 times of tau. Because each of these is tau t. So once I have that, then I could do the simplification. That's what I have here now. And I'll end up with e to zeta omega n tau t. Right, because the t1 there, those terms will cancel off. And then I'll take ln on both sides again. Take ln on both sides. So ln x1 over x3, and then that part there will come to zeta omega n tau t. So that tau t, as what you have seen before, that's 2 zeta and that omega n, and 2 pi over omega n square root 1 minus zeta squared. Very same thing that we have done just now. This and this cancel. So this is 2 times 2 pi, and I'll bring it to the left hand side. So 1 over 4 pi ln x1 x3 and zeta over square root 1 minus zeta squared. If you compare these two now, these two. That one with x1 over x2, and this one x1 over x3. What are the differences? It's only that coefficient. This coefficient is 1 over 2 pi. That coefficient is 1 over 4 pi. That is 2 pi comes out if you take x1, 2. 4 pi comes out x1, 3. So if you're to make a guess, if it's x1 over x4, what do you get for that coefficient?
8 pi.
1 over 6 pi. If it's x1 over x5, 1 over 8 pi, etc. Does it always have to be x1 and then something else? It need not. Yeah? If it's x0 over x1, what do you get? You get 1 over 2 pi. Yeah, so it depends on the combinations that you want. This is my way of saying, kind of like at a sideline. So in both cases, zeta will arrive at the same value. That means if you were to solve for this zeta, let's say x1 over x2, after you measure it, you know what it is, calculate it out. x1 over x3, if you know what it is, calculate it out. These zeta values for those cases, they will be the same value. So no matter which pick that you're taking. Now, you have seen before this thing about the spring that I showed you. So, if I have this spring that's oscillating, you know, after a period of time, it will come to a standstill, almost a standstill, and then it's still oscillating. Sometimes, as an engineer, we ask ourselves, I'm not going to wait forever until it stops. At what point of time, with that little bit of oscillation, and I can call it, I think it has to stop. Not exactly zero, but that little bit of oscillation, I can consider that it has settled. So the amount of time that you will go through, time take, the amount of time that you'll go through, until it comes to this little bit of oscillation, that amount of time that it takes, this entire time is called settling time, where it's more or less considered settled. What is that more or less settled? Is at this 5% of that highest amplitude. Some textbooks, they are more stringent. They say 2 or 3%. But over Glasgow, 5%, we consider that the system more or less is considered stop. It's still oscillating. 5% of what? 5% of the maximum first amplitude. Where is that first amplitude? That first amplitude is when you maybe quit, is this theta naught, and then release it, and then it comes back. That is your first amplitude, right? First peak. So the 5% that we are after is when it's extended at the maximum. So in this case, as it extended down, this is your theta naught. And theta naught is maximum, so that 5% is 5% of theta naught. Okay. Your lecture notes use either 1 or 9 theta naught. So if you follow this one, you'll be okay. Why I use this? Because I want it to be consistent with your lab. So 5% of theta naught. If it's rotary system. If it's not rotary system, that means it's a translational system. then you'll need x naught. So it depends on the system that you have. Is it like a spring that's going up and down, or is it a beam that's rotating? So 5% of that. So let's have a look at the expression. At time equal to infinity seconds, right? Infinity is for the case where the spring is keep on oscillating until time is infinity. So that is x equal x at time infinity. We must come to a standstill at 0 amplitude. Right? So this one means system comes to rest. That means it's not vibrating anymore. But practically, we consider the system to come to a rest within that plus minus 5% of x naught or even depending on what kind of system it is. So if I substitute into the equation x ts, and ts over here is my cycling time, I want to find out what is the expression for that cycling time. So that will be equal to 5% of x naught, right? 5% of x naught, that is 0.05 times x naught, equal to the amplitude, successive amplitudes expression. This x naught equal minus zeta omega n ts. Right. So this x naught could be cancelled. And then I take ln on both sides. Ln 0.05 must be equal to minus zeta omega n cycling time ts. So I can express ts as a subject. It's approximately equal to ln of 0.05 is actually minus 3. And then the denominator is minus zeta omega n. So the minus and minus sign means the settling time is equal to this expression. Settling time, Ts, is equal to 3 over zeta omega n. A few things to take note. This is only true for underdamped system. Right. For underdamped system, you have the system oscillating. So after a while, then you will settle. Your overdamped system don't really oscillate, so we don't talk about settling time. It didn't even oscillate in the first place. Your critically damped system also doesn't oscillate. So we only apply settling time for system that is oscillating. That is your underdamped system. The other thing to note, if I were to sketch out that just now you saw that way, right? And if I were to sketch that those two lines not very well in that way, right? So imagine this is touched. So if let's say plus minus 5%, they are here. Right. Plus minus 5%, they are here. So what I want to ask you is this. Settling time, you will start from 0. At which point do you think will be considered the settling time? Let's say this is touching. Point A, point B, point C, point D. This is not, it's also touching. But this is your plus minus 5%. A, B, C, or D. D is your settling time. Anyone say 8? B, C. Anyone raise your hand for D? Anyone like E? After the E? The answer to this is that is none of the above. Why is that so? Why is over here? X naught, this equation, isn't it equal to this? Yeah, this dotted line. And is over here. This equation is actually this line over here. So it's actually the intersection of these two. That is your cycling time here. Yeah, that blew your mind, right? Yeah. So it's nothing to do with where is it that's touching, not even this intersection. Nothing to do with this curve. It's between this and your decaying line. Where they intersect is the time that it takes until then, right? This should be in the same place, yeah? And that is your settling time. That's how we define it. So in your lab, we'll be doing this exercise, both calculation and experimental results. And you'll make a comparison. So actually today's class is the last class for the first topic. The first topic is about free vibration. Free vibration means that I will perturb the system and let it go anyway. Right? This system may or may not have damper in it, but it will definitely have spring or else it's kind of oscillate. So this is the first topic. There will be 4 topics. So today is the last day for the first topic, free vibration. So nothing beats a real exam question. Let's have a look at a real exam question. That exam question is in August 1999. Where were you at that year? Some of you kindergarten, that means you're very young. You're prodigy. You're prodigy. That means you're underage. You're an underage undergrad. Okay, this question, work example 2.5. Why I take this example? Because this is a real exam question. And then I want you to see how exam questions are set so that you're prepared. If you find that after working through this work example, you are still not prepared about it, then spend some time to prepare yourself so that you're more prepared. So these examples allows you to see the level of difficulty in exam question as an example. So I have some pictures. I think this one I'll copy and then I'll paste. Work example 2.5. So if you don't really know what is this thing that it mentioned in this work example, that is a railway buffer. So I can show you what is a railway buffer by showing you some pictures of railway buffer. Railway buffer